So now in this video we're going to look at a diagram I put together a while ago. My goal was to take circuits that I've covered before and to imagine powering them with a 12 volt lithium iron phosphate battery. So the main challenge is that when you attach a charger to it, a lot of chargers are rated for 14.6 volts. So I could apply this voltage to a lithium iron phosphate battery and it will charge. Ultimately, it will get up to 14.6 volts. Current will drop to almost nothing, and then you consider it completely charged. And then you remove the charger, and right away it should drop down to 13.6 volts. So that's the actual voltage of a fully charged battery, but you can apply up to 14.6 to get the most charge into it that you can pack into it. Not going to go into that into great detail. But if you have a circuit that you need to protect from a battery like that, you got to take into account that the charger will be attached from time to time, and some circuits would mess up the charging also. But in any case, we're not going to worry about that now. We're just going to consider we're going to light this LED even if it is getting charged. So worst case scenario, that's what we're going to plan for, 14.6 volts. Now we have an LED that's going to drop about 2 volts out of that. So while the charger is attached, we could get up to 12.6 volts right there. And to limit the current to about 13.4 milliamps, we could use 940 ohms of resistance, which is twice as much as 470 ohms. So we got 2 of them in series to get us that. And the reason why I did 940 was because we can take 2 of these in series. I didn't do a 1000 ohm resistor because it would get too hot. But when we have 2 resistors in series that are equal value, they're going to divide up that voltage equally. So out of that 12.6 volts, we'll have about 6.3 volts across each one of these. And there you can see that current again. And that will be the wattage. It's the voltage across each resistor and the current going through them. So when you got multiple series resistors, they divide up the voltage. So even though they have the same amount of current going through them as a lone one would, they don't have as much voltage across them, so they get a lot less hot. So now I got the multimeter. We'll take some measurements. 14.6 volts at the supply. That current's not as accurate as the multimeter will be, and even the voltage might not be as accurate. So we'll see we got a total of about 14.52 volts and a little bit less than 14.6. That's a little less than 2 volts that's being dropped from the resistors. So we have the rest of the voltage, about 12.6 volts right there. And that's going to be split up about equally right there. So this is a little bit low right there. So I think its resistance is slightly higher than this one right there. But they're cut, pretty close to being equal values there. Taken about half of the voltage that's left over after the 2 volts that is dropped by the red LED. And now I have a gap between the components that I put there so we can actually measure the current. And we're going to go to milliamps. I don't have to move the probe for anything except for high current for this particular meter. Low current, I can leave the probe where it is, and we have to bridge the gap. So remember, current is the same through series components, so now the meter is basically one of the components. And there you can see we got about 13.2 milliamps of current, about what we calculated. And it's going to change a little bit as things warm up, and also maybe as I make a better connection and stuff. So we had that current. Now let's look at the resistance. As I said before, I believe the first one, the one on top there, has more resistance. It doesn't matter which way we go down. So no current is flowing through there. We have an opening there, so we can apply the meter. Only the meter can put current through it. So yeah, that's a little bit lower than the 470 we expected. And so I thought that one would be higher. So we should not have got that to light up. That's very unusual. So there we go. Yeah, that one's actually the higher one right there. So yeah, this one should have had the more voltage across it. I think I may have got that wrong earlier. The higher the resistance, the more of a voltage would be across it when it's a voltage divider. So I think I got that backwards when I said it before, but that does make sense. The higher resistance of a voltage divider has most of the voltage, but they're still pretty close. So it's still about half, even with tolerances and these cheap components. Generally, you can grab the value that you calculate, and it'll be good enough. Now we are going to light the LED, and look, as I said before, this is like the charging current. The vast majority of the time it would not be this voltage, even if you had it attached to a lithium iron phosphate battery. When it's fully charged, the charger is removed, 13.6 is like the max it would be, and then a long time it will hover like 12.6 volts as you use it from fully charged to fully discharged. It really hovers in that range, and then when you get to about 12 volts you should probably stop using it at that point, but you probably won't damage it if you get down to like 10 volts. That's the absolute like minimum. Maybe the BMS will kick in at that point and shut the battery off, so you can't even use it. So you should avoid like 10 volts, but it is, you know, okay to go to 10 volts if all the cells are balanced and everything. But the vast majority of the time your voltage is going to be about 12.6. So you can plan for that in the circuits. The whole time the LED stayed lit for this circuit, even when we dropped to 10 volts, there was enough to keep it well lit there. So yeah, 12.6 is the nominal voltage of a 12 volt lithium iron phosphate battery, but there is a range, so you have to be aware of that. So in any case, that's it for this video. Thanks for watching. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.